Hello, my name is Beharry, and I'll be presenting on the paper titled Investigating the Effects of Process Parameters on the Flexural Strength of 3D Printed Plastics. For this presentation, I'll be introducing the topic with some background information, then go into the objectives of the paper, the methodology to achieve the objectives, the results obtained from experimentation and their interpretation. I'll finally close with briefly looking at the references, and all questions can be sent to this email address. To preface, I'd like to answer 4 questions. What is 3D printing? 3D printing is a relatively new additive manufacturing method used domestically and industrially for product realization, and is based on the principle of material extrusion through a nozzle under high heat and pressure. What are common applications? So 3D printing was mainly used for rapid prototyping, but is slowly being evolved to the direct manufacturing of final products for commercial use. Why is it important? To compete with traditional plastic forming methods, products made with 3D printing must have comparable or better mechanical properties, meaning research and development in this area is very important in making 3D printing a viable option for manufacturers to generate revenue and diversify the economy. What type of research is required? The key research areas include how the chemical makeup of the filament and the operational or print parameters being used in the process affects the mechanical properties of the final product. That is, strength, heat resistance, among others. This brings me to the objectives of this paper, which are to look at past research trends in a literature review to determine what materials, print parameters, response variables, and optimization methods were used previously in order to perform a gap analysis on the data to see where we can penetrate to add value to the data. Then we will want to develop an experimental setup, perform the experiments and collect the data, analyze the data, and then perform optimizations to enhance the mechanical properties going forward for manufacturers. Finally, we have to do some validation experiments on the optimized samples and make conclusions based on the outcome of the tests. So without delving heavily into the literature review, it was found that the tensile strength was the most commonly measured property for 3D printed samples, something sort of a benchmark test for strength. However, in order to maximize the use of 3D printing, products must be able to withstand forces in all directions. This will allow manufacturers to design and create products for a wider range of applications, while maintaining the strength desired for their use. As such, there seems to be a lack of information on the flexural strength of these products, which, if more understood, will allow for better design of products susceptible to deformation and buckling under compressive loads. Further, it was observed that ABS plastic was one of the most studied materials due to its extensive industrial use at a relatively low cost. So for this paper, the experimental setup includes using recycled polyethylene terephthalate, RPET, polyethylene terephthalate glycol, PETG, and polycarbonate, PC, samples, the process print parameters being adjusted for each sample, the layer thickness, infill percentage, and raster angle. The response variables being measured is the flexural strength, and some of the variables being kept constant is the brim, infill pattern, print speed, temperatures, the printer being used, and all accessories including nozzles, beds, etc. So for the experimental setup, we used a fractional factorial design in the Taguchi L9 orthogonal array. That is 3 parameters at 3 levels, low, medium, and high. The optimization technique being used is the genetic algorithm. The table in this slide shows the value or the level for each value of each level for each parameter used. This slide shows the sample set being used for the orthogonal array. Each sample set has a unique combination of levels, and these were used for each material. So for this experimental setup, we used the ESTM D790 standard in designing the samples, as well as the orientation of the samples on the testing machine. The figure on the left shows the sample design, all units in millimeters, and the figure on the right shows the placement of the sample on the Tinius-Olson universal testing machine, dimensions also in millimeters. On the machine, the loading pin applies a downward force, which eventually leads to the fracturing of the sample. The machine produces a load extension curve, which gives you the maximum force and the extension at which it occurs, using the formula in equation 1, where sigma F denotes the flexural strength of the sample at the midpoint, P represents the point load, L is the support span, B the beam width, and D the beam depth of the sample. This formula is used with the maximum load to determine the maximum flexural strength of the samples. The table shows the average results of 5 repetitions for 9 sample sets of each material. So what is to note here is the strength of the polycarbonate, or PC, was the highest, while the RPET and the PETG were similar in strength. Finally, the sample set 9 had the highest flexural strength. For A being the layer thickness, B being infill percentage, and C being the raster angle, nonlinear regression models were created for each material to model the experimental data collected to determine the relationships between the print parameters and the flexural strength. Residual plots and main effect plots among the 3 materials were similar in that the model followed the assumptions of normality and non-discernible patterns. Further, by the interaction and surface plots for the 3 materials, it was apparent that infill percentage had the highest impact on the flexural strength, where the higher the percentage, the stronger the sample. Finally, the raster angle had the least significant impact on the 3 materials. These equations fed directly into the genetic algorithm as the objective function being solved. The genetic algorithm, or GA, searched for the print parameters to produce the highest flexural strength, and using those values, which can be seen in the table, validation samples were printed and tested. From the table, it can be observed that the actual stress values from the validation experiments were lower than that predicted by the genetic algorithm. The RPET strengths were fairly similar, but the PETG and polycarbonate PC had a slightly larger deviation. This deviation may be attributed to the GA's inability to account for all uncontrollable or controllable factors that impacted the sample strength. There may have been some unexpected interactions between print settings not considered in the design of experiments that also affected the flexural strength of the samples. There may also have been some premature convergence to local optima, which caused the GA to stop simulating before a true optimal value was found. These issues may have been resolved if extensive work was done in testing and selecting optimal input settings for the GA to suit the data being examined. This should then be considered when doing future research using genetic algorithms or any other evolutionary method to determining optimal parameters. Nonetheless, from the analysis, print settings for maximum achievable flexural strength can be recommended. As you can see in the table, in general, it seems that the larger the layer thickness and higher the infill percentage, the stronger the product, while the effect of the raster angle may vary with each material. Finally, a brief cost-benefit analysis was performed comparing the sample cost in Trinidad and Tobago dollars to the strength of the sample. Clearly, PC has the highest strength of all samples, but also has the highest cost. Polycarbonate can be used where high compressive loads and rough external factors are expected, such as industrial housings or casings, exterior lighting fixtures, and furniture. PETG is a much more economical choice as it is much cheaper than PC, but also still relatively strong. For the recycled PET, the current cost of production may be high, but this is expected to improve as the recycling process is refined and optimized, and the cost of filament is reduced. Due to similarity in materials, RPET and PETG can be used for car parts, storage, and clothing. However, RPET also gives manufacturers an eco-friendly option that can be advantageous in producing highly desired products. All in all, to make the most of 3D printing, product choice and designs must consider the manufacturing process and limitations that come with it. By making suitable trade-offs, products with high customizability and adequate mechanical properties can be manufactured. This brings me to the end of the presentation. Thank you.